Hi friends, welcome back to my channel. Still on Power Machines N5. Today we are doing steam generation. My name is Tsepo. Please subscribe to my channel to make sure you keep on receiving videos like this, and click the notification button so you will be notified every time I post a new video. So today's business, steam generation. Steam generation, it's all about converting water into steam by adding heat energy into the water. The heat energy of steam is called enthalpy. Enthalpy, and is represented by the letter H, given by the formula U plus PV, where our H is our specific enthalpy, and it is in kilojoules per kg, and our internal energy is also kilojoules per kg. And then we have our pressure, which is kilopascal. Our volume, this is our specific volume, which is cubic meters per kg. Remember, H is the heat energy of steam. Now we know that the boiling point, this is what we were told, the boiling point of water is 100 degrees Celsius. But what we do not know is that the boiling point of water, it's only 100 degrees only if the water is subjected to a pressure of 101.3 kilopascal. So only when the pressure that is acting on the surface of the water, only when it is 101.3 kilopascal, which is the atmospheric pressure, we can say water boils at 100 degrees Celsius. So what I'm saying is that if we were to change this will also change. If the pressure acting on the surface of the water, let's take for instance, it was to increase, this will also increase. So 100 degrees Celsius is not the standard boiling point of water. It is the boiling point of water under atmospheric pressure, only under atmospheric pressure. If this changes, this will also change. So now let's erase this. Let's take, now we have a container. We have a container, and then we fire this container using an external source, and then there is water inside that container. This is what, H2O. And then we subject this water into a pressure that is atmospheric pressure 101.3 kilopascal, meaning now our boiling point will be 100 degrees Celsius. Our boiling point will be 100 degrees Celsius. And then we do not know the temperature of this water at this moment, but we know that the boiling point of the water, because it is subjected to atmospheric pressure, it's 100 degrees Celsius. And now we add heat to this water until it reaches the boiling point, which is 100 degrees Celsius. Now the heat that will be added to raise the temperature of this water until it reaches its saturation temperature, which is 100 degrees Celsius, it's given by HF, and is called the sensible heat. And then now the water is 100 degrees Celsius in temperature. The heat now that will be added to this water will no longer be used to increase the temperature of this water, because now the water has reached its saturation temperature, which is 100 degrees Celsius. The heat that is now provided or added to this water will now be used to turn this water into steam. So now the temperature is no longer increasing, but heat is being added. Now the heat that is being added to the water is used to turn this water into steam, no longer to raise the temperature of this steam. And then that heat that will be used now to increase, to evaporate this water is called, it's given by HFG, and then it's called the latent heat. And the first steam, number one, the first steam that will form will form now, it's called wet steam. Why is it called wet steam? It is because now the steam will contain water droplets, meaning that not the water inside this container will not have been completely evaporated. That's why we will have a steam that is wet, meaning that the steam, it is steam, but it contains water droplets inside it. And then the enthalpy of that steam will be given by, it will be H wet, and will be given by Hg, which is sensible heat, plus X, which is the dryness factor. The dryness factor now tells us how wet is the steam. Let's take you get a dryness fraction that says 0.9. This now tells us that in the overall capacity of the steam, only 90% of the steam is dry. The other 10% are water droplets. So if you get a question that says the steam is 15% wet, so now you can conclude to say now our dryness factor is going to be 0.85. This tells us how wet is the steam. And then our formula is given by HF plus X times FG. And then if you want to find the volume for wet steam, our volume is called V wet. It is equals to Vg. It is equals to X Vg. And then now we have the wet steam, but we keep on adding heat into the steam. Now we have steam, remember. We keep on adding, let's erase this. We have wet steam. Now we keep on adding heat into this steam. Now, because remember, the steam still has water droplets inside it, the heat now that will be added into this steam will be used to turn the water droplets inside that steam to water, so that we now have a steam that is pure steam without water droplets. And that steam is the second steam that is going to form from our steam. That's the second steam that is going to form, and it is called dry steam. Dry steam. And dry steam is given by a formula. It's Hg. The enthalpy of dry steam is given by HF plus HFG. And then our volume for dry steam is equals to Vg. This values you can get from the steam table under at a certain pressure, because now all our heating now are being performed at at constant pressure. So if you want to find the values of the dry steam, there is a steam table that we'll be using in this topic. If you have the pressure, you can go and extract all these values. And then now we have dry steam, but we still keep on heating now our steam. Now remember, we have pure steam now. There are no water droplets that needs to be turned into steam. We have pure steam. Now the heat that is added to this steam, now it will actually be used to raise this the temperature of the steam. So initially all our steams were at 100 degrees Celsius, but now our third steam, which is superheated steam, our third steam, which is superheated steam, it's superheated steam. Now it will have a higher temperature than this one, and then its enthalpy is H sup given by the temperature Hg plus Cp T sup. Now it's the temperature, the final temperature of the steam, which is superheated steam, minus Ts, which is the saturation temperature. In this case we are using 100, but this you can also get from the steam table when you have a pressure. This is the specific heat capacity for the steam, and then those are our three steams. To find the volume of our superheated steam, we will use a formula that says it's given by n minus 1 divided by n. Let's erase this. All divided by, says H sup, which is this value right here. Let me write it down here. H sup is equals to n minus 1 by n. That's our P. H sup minus 1941, and that's the formula for pressure of a superheated steam. So this is basically everything that we will need in this topic. And then in this wet steam, we can find X if we are not given by this formula, M divided by M plus small letter m. So the big letter M is the mass of steam, and then the small letter m is the mass of water. It's the mass of the water droplets inside the wet steam. So basically that's everything that we will need in this topic. So I have a question paper with me that we can do and see how do we apply all this information of under this steam generation topic. So the question paper, the statement, we are given a statement in the question paper that reads as follow. 3.5 kg of steam is expanded from 2000 kilopascal and 300 degrees Celsius to a pressure of 250 kilopascal. The specific heat capacity of superheated steam is 2.1 kilojoules per kg Kelvin. The steam is 10% wet at the later pressure. Calculate the total change of internal energy. 10% of this steam is water. Those are the water droplets. And then we can conclude to say now this dryness fraction of the steam is 0.9, which is the amount of it that is dry. And then they say calculate the total change of internal energy. Now we know that if this is 1, this is 2, they require us to calculate U2 minus U1. This is what they are looking for. So first we must know that we must put this in the right places. We were given 2 pressures, pressure 1 and pressure 2. And then we were told that the first pressure, the steam that is in the initial phase is at the temperature of 300 degrees Celsius. And then now, whenever you are given a statement like this, the first task for you is to find out which steam is dry or which steam is wet. In this case, it will be easy for us because we saw that the only steam that will have a temperature that is higher than the saturation temperature is the steam that is superheated. In this case, this steam we were given temperature which is 300 degrees Celsius, meaning that this is the steam that is superheated since we are given the temperature. And then we will go ahead and put this here, which is the specific heat capacity of superheated steam, kilojoules per kg Kelvin. And then meaning now that this is our wet steam with a dryness fraction of 0.9. And then we know the only way we can achieve this is if we go to the formula that says H is equals to P is equals to U plus PV, and then we are required to calculate this. But first we must find this which we have, our pressure we have, and then we must find volume which we do not have, and we must find enthalpy which we also do not have. Then let's start with the steam in the initial phase. We know that this is our superheated steam, and then we know that we can get our H soup. We want U here, and then we also want U here. We can get our H soup by the formula that says Hg plus specific heat capacity which we have, T soup minus saturation temperature at a pressure of 2000 kilopascal. And then now we go into our steam table and then look for Hg at the pressure of 2000 kilopascal, and then look also, since we have specific heat capacity and we have the T soup which is this temperature here, and then look also for the saturation temperature under 2000 kilopascal. And then I found that Hg is equals to 2797 plus our specific heat capacity is 2.1, and then our T soup is 300, and then our saturation temperature I found that it is 212.4. This is equals to 298. It's 2980.96 kilojoules per kg. Yeah, it's per kg. And then on this formula, PV, we know that we are looking for our U. We have this now, we have this, but we do not have our volume. So we must calculate our volume. We know that our volume is given by this formula. H sup, our formula for superheated steam, is given by N minus 1 divided by N all by P into brackets H sup minus 1941. And then we substitute our N, the value of N. If you are not given, like in this question, we use 1.3. That's the value of N. So we can go ahead and say 1.3 minus 1 divided by 1.3 all by, okay, let me write this here because I'm wondering whether you can see there. 1.3 minus 1 all by 1.3 into H sup. Our H sup is we have calculated it is 2980.96 minus 1941 divided by our pressure, which is 2000 kilopascal, 2000, and then our V sup we calculate, and I got that it is 0.12 meter cube per kg. Since we say this is our it is our specific pressure, specific volume, sorry. And then we are looking for U. Now we have everything. We can go ahead and make U the subject of the formula. Let's say it's U sup, and then we have H sup minus PV. That's also V sup. The sup is for superheated. Our H sup is this 2980.96, and then minus our P, which is 2000 kilopascal, times our V, which is 0.112, and then our answer is, I got what's my answer? My answer, I got 2740.96 kilojoules per kg. So now we have our U sup. This is our U sup, and it is equals to 2740.96 kilojoules per kg. So we are done with the initial phase. So now we must go to the final phase, where we will have to calculate also the internal energy. And then let's erase this. We know now that we are no longer dealing with superheated steam, but now we are dealing with wet steam. And then we also need to find our U, our H, which is enthalpy, and our V, since we have our pressure as 280. And then we come and say H of wet steam, that's equals to Hg plus our dryness fraction times our HFG at the pressure of 280 kilopascal. And then we go into our steam table again and extract the values of FH of HG and HFG at the pressure of 280 kilopascal. And then I've already did that and find that my values are for HG is 551 plus our dryness factor we are given is 0.9, and then my HFG is 2170, and then I got my H wet as 2504 kilojoules per kg. And then now we have this, but we still don't have our V. Then we can calculate our V, because we know that our V is equals to F is equal to X, which is the dryness factor, times VG, which is our specific volume, at P with H08 280 kilopascal. That's our pressure. And then we go and say and look for the value of VG at 280 kilopascal, and then our dryness factor is 0.9 times our VG from our steam table, which is 0.6460. It's equals to, then we calculate, and I got that our V is 0.581 meter cube. Yeah, that's our V wet. So now we have our X, we have our H, we have our P, and then we have our V. So we can now calculate our U wet. So first we must make U the subject of the formula. This is very important because it has marks. And then we get it as H wet minus P V wet. And then we put in the values of our H wet. First it's 2504 minus our P, which is 280 kilopascal, 280 kilopascal times our V wet, which is 0.581, and then we got I got our H wet as our U wet as 2341.32 kilojoules per kg. So that is the value of our H wet. And then we go and say, because okay, let's put, we know that the question, they said calculate the total change of internal energy. So we go and say our formula, U2 minus U1 is equals to our M, because now they are saying the total change in internal energy. Though these internal energies are our specific internal energies, this the question requires us to calculate the total, and then now we must times with the mass that we were given into our U number 2, which is wet minus our U number 1, which is superheated soup. And then we substitute our M is 3.5 all by our U wet is this 2341.32 minus our U soup. This is our U soup 2740.96, and then calculate. I got 1,398.74 kilojoules. It's no longer kilojoules per kg because now it is the total. It's no longer a specific internal energy. And then the second part of our question says, let's erase this. It says, state the three phases in which water can exist and give an example of each. So our second question, which is 5.2, requires us to state the three phases in which water can exist, which is solid, liquid, and then we have gas. So the examples, this is ice, for this is water, and then for this is steam itself. So that is that's basically the end of our lesson on steam generation, power machines, and 5. Hope this lesson will be of help to you. Please comment below and tell me what you think about today's lesson, and yeah, don't forget to subscribe, like this video, and share it with others. My name is Tepo. I will see you in the next video that will be on throttling of steam. Ciao.